lots of differential equations and the matrices. Well, at this point, we are moving back our topics to the discussion of differential equations. So we are in chapter 4, and specifically chapter 4, mostly it is a discussion of second order linear differential equations with constant coefficients. I'm having those two sections combined together, 4.2 and 4.3. Okay, so let's take a quick look what are the second order homogeneous equations with constant coefficients. Well, I do have the general form right here. It is in the fashion of a y double prime plus b y prime plus cy equals 0. And if you are confused with all the notations, first of all, about y, remember in the discussion of differential equations, usually we assume y is a function of time t. So this assumption it is still true. And y is a function, then y prime is a derivative, y double prime, it is a second order derivative. Then for a, b, c, those notations, they each for constant. Each of those notations is for constant. So for example, we may have 2y double prime minus 5y prime plus 3y equals 0. It is homogeneous because the right hand side is 0. This is also homogeneous, and indeed they are all homogeneous. In the first case, the coefficients of a, b, and c are 2, -5, and 3 respectively. Okay, for this differential equation, the coefficient for a is 1. And note here, there's not the y prime term, but you can consider y prime has a coefficient of 0. So this is exactly the case for the second equation. B is 0, then C is 1. Okay, actually, I should write this as y double prime minus y, not minus 1. And the last equation looks like there are no coefficients, but anyway, I hope you see there are coefficients. Each coefficient is just a sign, 1, 1, 1 here. So all these are the so-called linear second order homogeneous differential equations. Homogeneous differential equations. Besides the coefficients of y, y prime, y double prime, they are constant. So this is a kind of long description for the differential equation we are working on. Before we solve this type of differential equation or provide solutions, it is very helpful if we review something very simple. Indeed, I'm talking about a quadratic equation. And keep in mind, a quadratic equation always can be solved using a quadratic formula. And also, indeed, we do insist, we say a quadratic equation must have two solutions. And then the third degree polynomial must have 3 solutions, fourth degree polynomial must have 4 solutions, and so forth. Okay, so this is a basic review about basic algebra, quadratic equations. Actually, I provided some example here. Example 1. Well, consider this is a quadratic equation, right? Not a differential equation at all. So I have 2x squared minus 5x plus 3. And indeed, it can be factored. And also, if you want, you can always use the quadratic formula. But probably you see it takes a little longer. Besides, you really need to remember the quadratic formula all the time. So what I did, it is factorization. And again, it does confirm for a quadratic polynomial, there are 2 solutions. Second one, I have another quadratic equation, and still make sure you know there are 2 solutions. Hopefully you see 1, but don't forget -1, it is also solution. And another one, I labeled that same example, part B, because they may look similar. x squared plus 1 equals 0. But you may want to know it cannot be factored like we did previously. But we can solve it using the complex number. And if you are not familiar with the situation, I do have a reminder here. The complex number has an imaginary unit. So the imaginary unit is I equals the square root of -1. And so accordingly, there are two roots, I and -I. And also, I hope you know, for those two complex roots, actually for each complex number, there's a real part and the imaginary part. And so I said the real part, there's no doubt, it is 0. There's no real part at all. The imaginary part, you could say that's 1 or -1. But anyway, later on, I just want to make sure, you know, indeed for the imaginary part, usually we just take the positive value as for the imaginary part. The -1 part really doesn't matter. And another quadratic equation. In this case, all the coefficients of this quadratic equation equal to 1. So we use the quadratic formula, and we got two complex roots, x sub 1, x sub 2. And hopefully this is a lot clear. We say the real part is -1/2, and the imaginary parts, well, this part is positive, that's negative. And again, I want you to know later on, we really don't make a difference for the positive or negative imaginary part. For the imaginary part, we always can take the imaginary part as positive, okay, positive. So far, I think that's all for the reviewing for quadratic equations. Actually, one more problem. The quadratic equation in this fashion, and indeed in this case, I hope you see that's a perfect square, right? X squared minus 2x plus 1, and it is x minus 1 squared equals 0. And indeed in this time, really truthfully, there's only one root, 1. But we said in the beginning, a quadratic equation must have two roots. So we say this root, it has a multiplicity of 2. This root has a multiplicity of 2. Okay. That is about the quadratic equation, the reviewing of quadratic equation. And then you may wonder, what is the connection between the linear second-order differential equation and the quadratic equation? Probably already observed. Indeed, I did use the same notation for the quadratic equation and for the differential equation, I mean for the coefficients. Indeed, we could match each differential equation in this fashion with a quadratic equation. That quadratic equation, it is the so-called characteristic equation. Okay. And then the differential equation can be solved according to the solutions of the characteristic equation. And indeed, at this moment, well, because we are considering the second order linear differential equation, so accordingly, the characteristic equation, it is always quadratic. Okay. So maybe do I have any simple and easy examples to finish? Or maybe just to present the general conclusion first. Okay, I said the solution of a differential equation can be generated according to the solution of the corresponding characteristic equation. Certainly when we have a second order differential equation, we're going to have a quadratic equation. And as we just discussed, a quadratic equation may have two solutions, okay, two real numbered solutions. So if that is the case, you may want to know the solutions can be generated or as the solutions, or let's just use the plural form. The solution, indeed, there are many solutions. So the solutions, they all can be represented by using this linear combination. E to the R1t plus the linear combination of e to the R2t. This is the first case when the corresponding characteristic equation has two different real roots. And also remember we said a characteristic equation or the quadratic equation could have one single root, right, with multiplicity 2. So this is the second case as I typed here. Okay, when you are having really one solution with multiplicity 2, and you always can find out the solution using the quadratic formula 2 if you want, or indeed it's a lot easier if you consider factorization, because in the factorization it is always a perfect square. Okay, so we always can find out a single solution with multiplicity 2, and then if that is the case, what you are going to have here is you are going to generate two exponential terms, e to the rt and e to the rt. For the second e to the rt, you want to multiply it with a variable t here. Okay, e to the rt and t times e to the rt. And so y is the linear combination of those two different functions. By the way, I hope you remember the concept of linear combination. In our previous discussion, we also said that functions can be vectors. Okay, so I'm saying those functions, they can be considered vectors. So it makes sense. We are having a linear combination of linearly independent functions. There are two linearly independent functions. And one more case. A quadratic equation may have two complex roots. So if that is the case, pretty much that's the complex roots from the same quadratic formula. And then you want to identify the real part and the imaginary part. And as I mentioned, the real part, there's no issue at all. For the imaginary part, if you remember the other examples I mentioned, there could be positive or negative imaginary parts, right? What you can consider here is, for the sake of differential equation, you really only need to consider the imaginary part as positive. So that's what I did here. It is always positive, okay? It is always positive. And then if that is the case, the differential equation can be solved as this fashion. The exponential function, e to the alpha t, alpha is the real part, times parentheses, the linear combination of cosine beta t and sine beta t. Beta, it is the imaginary part, and it's safe to say beta is positive. So I hope you see the connection between the second order linear homogeneous differential equation with constant coefficients to its characteristic equation, which is a quadratic equation. Thank you for watching.